Alright, well, welcome back to part 2 of my Kerbal Space Program Let's Play series. In this one, I'm going to show you a bit about how orbital dynamics work. Orbital physics just don't make any sense to us land-loving humans with our squishy meat brains. So there's some counterintuitive things involved here, but once I explain them, hopefully they'll make a lot more sense. So we've got a fairly standard rocket here. It's a 3-stage ordeal with some solid rocket boosters just to get us off the ground, and then a liquid-fueled engine in the middle, followed by a third stage, the upper stage here, which will allow us to manipulate ourselves up in orbit. So without further ado, let's get going. Oop, there we go. Alright, so we've established our apoapsis above the atmosphere, significantly above the atmosphere, because we want lots of room to be able to maneuver up there. So we'll just zoom until we get about most of the way there, and then we'll do our circularization burn. Alright, now we're all the way up here, going to start circularizing our orbit. So we'll aim in the direction that we're traveling, so basically forward. And you'll note the space center back down there. And firing the engines. The ascent stage is exhausted. Just ditch it. It should fall back to the ocean. And fire our orbital stage. Cat. Right, and then we just need to burn until our orbit circularizes. You can see our descent vector is getting further and further away. Eventually it will get so far away that we won't be able to hit the planet. Meow. Cat is meowing. Et voila, we have reached orbit. Now I shall pause to see what the cat wants. So now that we're in orbit here, we've got the luxury of time since we're not about to fall back to the planet anytime soon. So let's try out a couple of things about how orbital dynamics work that might be a little bit counterintuitive based on our ground-based understanding. So if we were wanting to go, like, up, you would expect that you'd want to stick the ass end of the spacecraft towards the planet and burn out. So let's try that. Let's see what that does. So we start burning, and let's have a look at the map here and see what our orbit's doing. Well, that's strange. The apoapsis is definitely getting higher, but the periapsis is getting lower. So as we're burning up, we're actually in danger of hitting the planet. So let's not do that. So let's do the opposite. So we'll burn back towards the planet. And this way we're burning, like, straight down, but we're not actually getting any closer to the planet either. Our apoapsis is definitely going down, but our orbit is actually moving from, like, left to right rather than up to down. So now that we're back basically in orbit, let's see what the other things do. Now, how you actually want to go up and down is by going prograde and retrograde. So prograde means in the same direction as you're currently traveling, and retrograde means, well, the opposite. So if we were to burn in the direction that we're traveling, you'll see that our apoapsis starts going upwards and further away from us, of course. So that's how you actually get higher and higher, is just by going faster and faster. So conversely, if we point retrograde, so opposite to the direction of our travel, and then start burning, then our apoapsis starts coming down, and that's how we'd actually get back out of orbit. So as we were going up in the first place, we were doing so by going faster and faster, so that we're moving faster than gravity can bring us back down to the planet. And then if we wanted to get back out of orbit, then we'd have to go slower so that gravity can grab us and bring us back down again. Because gravity still has us. Like, the gravity at this altitude is still like 90% of what it is on the surface. The only difference, the only reason why we're still up here is that we're just moving so fast that gravity can't get us down into the planet fast enough before we start missing it. Now, when we were trying to change planes on an orbit, such as if we wanted it not to just be around the equator, but if we wanted to go around from pole to pole, for example, we'd have to burn, as you might expect, perpendicular to the direction of travel. So if we're currently going this way, then we'll want to try and burn that way. Now, this does take an awful lot of energy, and I've currently got infinite propellant turned on because it would be otherwise impossible for a craft of this size to do this. Now, this is why when we're launching polar satellites, we don't actually do it like this. We don't burn into an equatorial orbit and then try and get it to a polar orbit. There's actually a more complicated way of doing it that saves a lot of fuel in the long run. So as you can see, this is going to take quite some time to get us to the polar orbit that we were after, but let's not bother doing that. Let's actually just switch back to the other direction and we'll get back to our equatorial orbit after a few moments of burning here. And I'll show you a couple other things. Now, the other interesting thing about orbital dynamics is that the efficiency of your actions highly depends on how fast you're going. So right now in our standard orbit, we're currently going just over 2 kilometers per second. If we were to burn prograde to raise our apoapsis, we can do so pulling it out to around, I don't know, let's pull it out to 500 kilometers, thereabouts. So with it now at 500 kilometers, you can see we're in a fairly elliptical orbit. Our periapsis is only 180 kilometers versus our apoapsis is 520. So let's just warp around to that. So now that we're at this higher altitude, you can see our speed has actually dropped. We're down now to 1600 meters per second, whereas when we were back down here, we were over 2000 meters per second. Meanwhile, if we were to burn retrograde here, it would actually have much greater effect on our periapsis at this altitude, given how much slower we're going. So if we were to burn backwards, you can see that our periapsis very quickly drops below the planet's surface, which would take us out of orbit fairly quickly. We don't really want to do that quite now. So let's bring us back up. And the reverse of this is true as well. So let's warp down to the periapsis. And at this level, us traveling at almost 2,500 meters per second, if we were to burn prograde, our apoapsis would raise much higher, much quicker than if we were going slower than this. So you can see we can bring it all the way out to 1,000,000 meters. And likewise, if we were to go out to that 1,000,000 meters, we could move that periapsis even faster than we were before. Now, if, however, we were somewhere in between, somewhere right in the middle, it would actually be difficult to do either one of these things. If we were to burn prograde to try and raise our apoapsis, it wouldn't just raise our apoapsis, it would also raise our periapsis because effectively the thrust is being split between these two points of the axis. So burning prograde here, you can see the periapsis starting to raise, the apoapsis is starting to raise, and we're becoming more and more, elliptical as time goes on. Now, we haven't really accomplished as much as we would have with the same amount of fuel if we'd done so either at periapsis or apoapsis. So when we're trying to raise or lower your periapsis, you want to be as high as possible, which is to say as slow as possible. Whereas if you want to raise or lower your apoapsis, you want to be going as fast as possible. So you want to be as low as possible on your orbit at the periapsis. So if we were wanting to get to the moon, for example, we'd want to do so from the periapsis, because if we were burning from the apoapsis, well, it would just be so much less efficient. Now at this point, though, we don't really have a craft that's capable of getting to the moon and back again, especially if I wasn't using the infinite propellant cheat here to be able to demonstrate this stuff. So we'll just bring it on down and I'll design a different spaceship which can get us to the moon. Here we are out at the apoapsis. We're going to burn very slightly to bring our periapsis down into the atmosphere. And there we are. We've got a periapsis of 48 kilometers, which is well within the atmosphere. And so as soon as we hit the atmosphere, it will start bringing us down to the planet. So we'll just zoom until we get there. Alrighty, and now that we're into the atmosphere again, we'll just we'll just be heading back into the planet at a fairly quick rate. Since we've got a little extra fuel left here, I'm just going to go ahead and burn off some of that extra velocity, which should get us down in a more gentle fashion. Alright, and now that that is exhausted, just going to go ahead and ditch that. Point our ass back into the wind here. And just wait for the heat shield to burn off all of our excess velocity. Ta-da! We've arrived back. Do a little more science here and recover the vessel.